We are live. It is 4 p.m. Central European Time here in the beautiful Netherlands. We are all over the world today with companies in the United States of America and Asia, and of course in Europe. Welcome to EPIC. Welcome to the online technology meeting on pluggable transceivers. In the previous online technology meetings, we studied the growth in data communication demands for a new connected world. With the big players in the industry, we have identified business opportunities in the supply chain, and we've realized that the big one is developing the right transceivers at exactly the right time. For that, companies like Intel, Luxtera, Nokia, Effect Photonics, Sequoia, Scaling Optics have developed fantastic solutions by combining integrated photonics with electronics. They satisfy the form factor demanded by equipment vendors. So what challenges lie ahead? Well, a paradigm shift in data networks is coming, and we saw in our online meetings 800G may not satisfy upcoming demands in the medium term. Onboard optics and even co-packaged optics may only be an intermediary step in the future integration of motherboard and optical components. So let's do what we do best at EPIC. Let's bring together the beyond 400G equipment vendors, the transceiver manufacturers, and their supply chain. That includes photonic integrated circuits, micro optics, VCSELs, electronics, assembly specialists, and let's answer the EPIC question. So switch on and plug into the EPIC online technology meeting on pluggable transceivers. Let's do Datacom business. Let's do Datacom business this beautiful afternoon. I recorded this video just before my holidays. I made a couple of statements on that video. You cannot imagine how many people sent me emails during the holidays saying, are you sure you're saying this? Are you sure you're allowed to say this? And a couple of people actually told me, do you have the guts to say that? That's actually fascinating. So I love that. And thank you all of you for the great feedback. And of course, I like to have fun at my job, so I can make any claim I want. At the end of the day, I don't sell transceivers. I'm sorry, I also don't buy transceivers. But let's talk about what we have in our hands today. We have a huge opportunity for making business. The EPIC technology team has worked extremely hard on bringing the who is who in the whole entire supply chain of photonic integrated circuits, pixels, and electronics, all the way to the huge system integrators. First of all, I would like to thank the EPIC members. We are now 600 companies. We are now 600 companies in EPIC, and without your support, we couldn't do anything. This is the second chapter of the season 2. This is like a Netflix show now. Season 2, chapter 2 of the EPIC Online technology meetings. Today we talk about transceivers. We have already the plan until Christmas. If you see any topic that interests you in the upcoming online technology meetings, all you have to do is register online or simply send us an email, and we'll be happy to engage you on that particular meeting. I would like once again to say that I'm part of a dream team. This is the dream of a lifetime, to have people that I really love working with. This is my team. Half of them have PhDs, the other have know the industry and the marketing extremely well, and we are here to support the 600 members. We organize events, we provide access to a network. Please tell us which companies you want us to introduce you. We'll do that. We help companies raise capital, and we have the biggest website in the world. I'm going to repeat that. The biggest website in the world in finding a job in photonics, www.jobsinphotonics.com. And we also, all of you know this, we have a lot of market reports in our database we give for free to all the members. But today, we are not here to talk about EPIC. We are here to talk about pluggable transceivers. I would like to say thank you so much to COBO, to the Consortium for Onboard Optics. Without you, we wouldn't be able to bring all the entire supply chain all the way to the users. Brad Booth and all the COBO family, you are EPIC VIPs for life. Thank you so much for this. I also would like to thank the sponsors today. Without you, this meeting wouldn't be possible. Sabic, the company, the huge company in the petrochemical industry. If you are looking for extend lenses in harsh environments, this company can provide you the material for making the optics for harsh environments, from consumer all the way to automotive. Effect Photonics, one of the success stories of the European ecosystem, indium phosphide-based modules, from transceivers to self-tuning modules. This company has made success out of a great technology. Congratulations, Effect, on all what you are doing for the European industry. Rockley Photonics, who doesn't know Rockley Photonics? Thank you very much for your support. Any company that is looking for solutions in silicon photonic integration, all the way to supplying in the telecom, datacom, but also in the sensing industry, Rockley Photonics is making a huge difference. Aextris, when you are looking about micro optics and optical systems based on micro optics, aextris has great technology to support you. And finally, ficonTec, the company has positioned itself in the center of the supply chain of photonic integration, providing assembly solutions, assembly equipment for packaging and assembly optical instruments. And now I'm going to give the floor to my good colleague and better friend, Ana Gonzalez. Ana, thank you very much for being with us. What's in the menu today?
Thank you, Jose. I couldn't wait for this moment to arrive. And finally, here we go. And here you can see the list of companies that are going to give a talk. And this will be very useful to trigger the discussion between the entire supply chain that you can see here. I hope you agree with me that this is one of the most amazing lists of companies put together in any kind of virtual or physical event. So we have the service providers, we have a transceiver, the companies doing transceiver modules, a vertical integrated networking solutions. We have all a great part of the supply chain for photonic integrated circuits, also for packaging, assembly and testing, VCSELs, semiconductor lasers, IoT connectivity software, and also, just a last mention about the pilot lines, which we are collaborating. JPIC's pilot line for going to ramp up the production for indium phosphide chips, also picks up for packaging and assembly, photonic integrated circuits, and Passion for that is not a pilot line, but is an innovative project that is developing metro network solutions. So that's it. Let's start, Jose.
Thank you very much, Ana. It's so great to have Ana in EPIC. Ana loves photonic integration even more than me. And now we are going to say hello to the people in YouTube. This meeting is being live streamed in YouTube. So hello, YouTubers in the world. If you want to get in touch with any of the companies in the Zoom room today, all you have to do is send me an email, jose.pozo@epic-asoc.com. I'll be happy to make that introduction. This, of course, is also valid for the people in the Zoom room. If you want to get in touch with each other, all you have to do is, of course, use the internal chat provided by Zoom, or simply send me an email saying the company or the person you would like to be introduced. I'm so happy to make that introduction. Almost as happy as I am to introduce the next speaker today, who is also a very good friend of mine and also a person who is not afraid of making claims like I am not either. Mark, all the way from the beautiful US of A, thank you very much for being with us this beautiful afternoon here in the Netherlands, this beautiful morning for you. The floor and the attention of everyone in the whole world goes to your living room. The floor is yours.
Thank you so much, Jose. And I think Anna's getting my slides up. There we go. And, you know, maybe I'm becoming an old fogey. I don't know. There's I would say in the world in general, a reckless disregard for the truth. And I think, you know, given that we're in technology and science, and we ought to be careful about that. We ought to be careful to sticking to facts, not make science political science. And there are just too many narratives in our industry that just stick around for too long. Can we go to the next page, please?
And I think we are not full screen with
Oh, somebody has control of the next page. There we go.
You're sharing the wrong screen, Anna.
So can everybody see that slide?
Yes, we are going to solve it in 1 second, Mark. As I say, yes, it's true that this industry is getting full with marketing statements. We are here to find out what we can do for each other. And I always love when Mark takes the floor in the beginning and place everybody in the right mindset. Let's try to find each other, to make us each other a little bit uncomfortable, because this afternoon we don't want to fall asleep, but also let's try to make each other work together. That's what we want to do here. Anna, can you change the screen that you are sharing, because you're sharing the wrong one? Otherwise, just unplug the second. Yes, I think we are in business now. Not yet. Let me see.
First of all, I'm going to mute myself because I couldn't before. Okay, share screen.
Yes.
And
we are going to solve this in a second. Everybody is
Presentation is solved.
smiling. Gloria is there from Infinera, my friend Gloria. I love you, Gloria. Thank you very much for joining today. I think we're in business now, Anna. Mark,
Yes.
the floor is yours.
Thank you. We go to the next slide, please. I hope.
Now?
Okay, thank you very much. So, you know, some of these narratives, you know, never go away. You know, I was saying since 2010 that Google Fiber shouldn't have been taken seriously, that it was just about getting other operators to do likewise, to bring more bandwidth to the table. I also think, you know, there were other reasons, you know, there was CLEC, so in case Verizon or AT&T decide to kill the internet for whatever reason, you know, the 1,000,001 chance they do that, they could say we became a CLEC in good faith and they shouldn't do that. Verizon in particular, you know, I don't play favorites with any company, but for whatever reason, you know, it was crazy with Fios apparently, and I agree. At the time they were doing it, the cost was extremely high, and they deserved to get some grief. But because, you know, they're regulated, they couldn't afford to tell everybody that they were passing every Fortune 2000 customer along the way to pay for it. And Verizon gets hit a lot. They obviously make mistakes like every other company. Even when it comes to millimeter wave on 5G, you know, T-Mobile supposedly has nationwide 5G service in the country, but supposedly Verizon is doing the wrong thing, and by stressing millimeter wave right now, and I think that's just totally wrong, that point of view. And actually, we'll be putting out a report, you know, giving a legitimate rationale, you know, for why Verizon is focusing so much on millimeter wave. But I guarantee, I'm 99% sure that won't change the narrative, but I'll do the best I can. Can we go to the next slide, please? Thank you. I mean, you know, we've been talking about 400 gigabit Ethernet for a while now, maybe a good 7 years. There's a market research firm who will remain nameless who said there would be 1 million 400 gigabit Ethernet modules in this year, actually. So you know, it's been taking a while, and you know, we need to keep these things in perspective. You know, and putting aside the fact that there's all this talk about you know, going to 800 gig or beyond, we're just in the beginning stages of 400 gigabit Ethernet. And I think if you remember Jose's presentation, he's pretty much saying that we're making a transition to that. Broadcom is just ramping up. You know, that is nothing negative about Broadcom, and so you know, that's going to take a while. But the main point is that for several years, the main concentration in this market for the hyperscalers, it's going to be for 100 gigabit Ethernet and 200 gigabit Ethernet. 200 gigabit Ethernet in particular, because you know, the cost is getting so low, it's becoming competitive. You know, close to the cost of 100 gigabit Ethernet. And so at the end of the day, you know, these the hyperscalers talk a good game about needing all this extra capacity, but in the final analysis, they stay at lower rates and commoditize it and do whatever they can to lower the cost and that sort of thing. We also put out a report on 400 ZR, if I may say so. It's an excellent report. We were accused at the beginning of being of our numbers being too small. And even one of the vendors, I believe, NeoPhotonics, excuse me, is saying that, well, the market size could be 500 million, 100 million. We took about 45% of the 500 million, and so we've been getting some grief over that, or at least initially. For one vendor in particular did especially like that. What had happened is, even before the market's really taken off in a big way, you have a Chinese vendor that's come in on pricing that's just way lower than the initial expectations. And so, you know, we actually might wind up being high on our numbers, which is not uncommon. You know, in the final analysis, these research firms could talk about having these models and all that, all this other stuff. But it really comes down to gathering a lot of good intelligence. It really comes down to a gut level feeling. The ZR Plus may take a while. It's kind of a Swiss Army knife. It will have longer distances. And of course, we're talking about the line side here with 400ZR, DCI, and metro types of applications. So ZR Plus may take a while. I don't think enough is made with even at 400 gig. There's starting to be this discomfort level with power. 800 gig, the power problem becomes really relatively large, and so that has to be taken into consideration in going to these higher capacities. If for whatever reason and going beyond 800G, whether it's the polymer guys or whoever. For some reason, the Shannon limit doesn't come up, but whatever. And the web scalers, they have this tendency to want to scale in the same way as servers and storage, and optics is just different. And I think that's just unreasonable. I think it's just unreasonable to expect that to happen. Even at, and I don't think most of us thought it would happen. I mean, they did get to $1 per gig on 100 gig. And, even then that supposedly wasn't sufficient. So, it's very interesting about that. If we're talking about the standard IEEE stuff, I'm saying 400, 1 million, the first million in 2026, that may sound overly pessimistic. I just think it's overly complex and it'll take a while. At the same time, the argument's made that the devices will be simpler despite the complexity. So that's a little confusing. We'll see what happens there. But there's no doubt that the next step is to double the 200 gig and to get the 400 gig. And just like what happened with, of course, with 100 gig, it was also the fact that you had the traditional carriers, paying, getting down the cost. But it's really the Chinese vendors that have lowered the cost substantially on the 200 gigabit Ethernet and will do so on 400 gigabit Ethernet. We can go to the next page, please. So, given that this is all going to take a while, the 400 gigabit Ethernet to take off, given that we're just in the initial stages, Broadcom, in a big way, or just starting to ramp up. The fact of the matter is, and this is a point that was made in an earlier presentation or an earlier virtual webcast with Epic, that CPO is going to be the intermediate step, that we need to have true integration, and there's no doubt there's been problems with CPO, that it is this hybrid kludge, and that new developments will need to be made. But even when we get to 100 terabits, boy, I don't know, 50 pluggable. I'm still betting on the pluggables there. Let alone the 50 terabit switch. And the problem is, if you look at a Microsoft, which is still, for whatever reason, no offense, I mean, they are a sponsor, but once you get the CPO, I don't know why you necessarily need to have COBO anymore, but I think vendors are going to feel obliged to at least give to have some allegiance to COBO in order to ensure that they get business. So what you have in effect are three solutions that need to be developed, with the vendors assuming the total risk. And in the final analysis, the hyperscalers might wind up doing all of this anyway, as they're moving to switch chips, and they have the resources to do it. So it's a risky proposition. We go to the next slide, please. So, I mean, this is hazardous. I mean, yes, it's exciting. Don't get me wrong. I mean, the four big hyperscalers, they are tremendous companies. I'm proud that they are American companies. They're helping to bring the economy back during this COVID period. But I always get the sense there are bean counters at the top, and then you have the network planners, and the bean counters are just kind of looking at it and saying, well, we're just using we have such enormous costs and gradually such more power being used. And, we need to do something about that, especially, again, in comparison to storage and servers. And I just think that's unreasonable. And I also think it's ironic because, some of these hyperscalers, their track records are mixed. Some are better than others. I don't think they do adequate benchmarking when they are looking at new solutions. That gets eliminated in the total numbers. So nobody looks at that. But when you're staring at the cost of fiber, or the cost of optics and the power, that's right in your face, and they need to do that. So essentially, the network operators or the network planners and the architects that are involved with these optical networks, they're between a rock and a hard place. They can get fired now for not listening to the bean counters, or they get fired later when possibly what happens is you stick a pluggable into a white box and you use your own sourcing power. Maybe there's a reliability issue there, and so there could be a time when we have an extensive outage by one of these cloud guys, if not a security type of thing. And maybe we see a return to companies doing their own data centers and that sort of thing. So we'll have to see if that happens. But my general point is be very careful about the hyperscale, getting into the hyperscale vortex. These companies are very attractive in terms of their size and their reputation. But if you could possibly avoid it, and you're not a Chinese transceiver provider, I would recommend you avoid it. And that's it for me.
That was the best way. If you are not a Chinese transceiver provider, that was something to quote you on, but thank you very much, Mark, for a fantastic introduction to what's going to be an epic world of discussions. That anybody has a question, a statement, or something to comment on Mark's presentation? There is a person in the room who I know has something to comment because it's a person who has followed the trends over the last 30 years of packaging of transceivers, and a person I strongly look up to. Is one of the key people in the Epic network, Bob Musk. Thank you very much for joining this beautiful meeting today. Bob, how are you doing today?
I'm very well, thank you.
What is the picture that you have behind you?
That's where I live. In fact, over that hill is where I am right now.
Wow, it looks fantastic. You have something to tell me about the packaging of transceivers, is that right?
Yeah, what I'd like to do is just show you a little bit of the history. It's been going on for about 30 years now. 30
years, and what have we accomplished?
Well, let me just share the screen and I'll show you what's been going on.
Bob is one of the people who we have been interacting over the whole online technology meetings over the last months, and he's been extremely helpful on telling us what has been the transition from the previous years until now. Bob, we can see your screen perfectly clear.
Right, well, Jose just gave me 1 minute to do this, so I'll be as quick as I can. So this is just looking at the background history of the pluggable optical transceivers. It goes back to 1989 when BT&D developed transceivers for the DuPont Matrol backplane system. And I believe these are probably the very first pluggable optical transceivers. Then in 1995, the first commercial pluggable transceivers with the GBIC, followed shortly by Zenpack. Then if we look at the small form factor NSAs, this is going back to 1997, the original devices were pinned. that caused a lot of the customers problems with trying to mount the boards and solder them in place. So the request was, can we have surface mount, please? And all the MSA members looked at it, but unfortunately, IBM's optics at the time wouldn't survive surface mount temperatures. So we had no option to look at an alternative and that was to use a pluggable device. That way we got over the problems for IBM, but the pluggable device then was chosen as an alternative to SMT, not because of its pluggability, etc., which I think is an interesting twist. And if we look at some of the very first pluggable SFP proposals, it's just two of them here, one from IBM and one from AMP, and the one from IBM is based on a slide connector rather than a pushing connector, such that AMP proposed. And then if we just look at all the pluggable transceiver module formats, there's a whole wide range, and this is just a summary. It's not all of them. It just gives you some idea of the variants that are out there. And that's it. I've done it. I think I've done your minute for you.
Thank you very much. It was a big challenge because you sent me a lot of slides and I told you, can you do it in 1 minute? And you managed to do. I think we have set up the ground to get the meeting going strong. Brad, what do you think? We have already told you what the landscape looks like, what the history look like, and now I'm going to the key company in the onboard optics alliance and also the key company in the Epic Heart Microsoft. Brad, thank you very much for being with us in this beautiful morning for you, beautiful afternoon for us. What's on your mind?
Yeah, hi, Jose. And good morning, good afternoon to everyone who's participating. You know, I think Mark and Bob have raised some interesting aspects when we talk about pluggables. And this industry is very different in the fact of what we used to think as optics and how we're using optics. You know, Bob highlighted how we moved to pluggables. You know, if you look at it, originally, most of the optics actually were onboard optics. And I think, you know, when they say like everything old is new again, I think that's one of the aspects of, you know, what it really is a pluggable. You know, is it something that I'm inserting? Is it something that I'm embedding inside a system? Or is it what we're going to be looking at in the future here where, you know, I might be doing some type of co-packaging and it's pluggable on an MCM? I think the aspect to understand for a lot of this is, and interestingly, Bob did touch on this, was power. We do have very different thermal environments depending upon how far someone wants to drive something. If you're driving within a rack or within a row, the requirement for power there is significantly less than if you're trying to drive metro or subsea links. And so something that's doing, say, a co-packaging, that device is not likely to be driving a subsea link, but it could be driving, you know, a disaggregated link. And that's a critical element here, because what's happening is when you look at building data centers, the power we pour into them is a tax, and we don't want to necessarily have to build another data center. And so the way I can keep that power down while still providing the end users the applications and everything else that they need helps me, you know, not have to move and build a new data center, which, you know, they're a significant investment. You know, it's billions of dollars. It's like building, I remember when I was at Intel and they used to talk about building fab facilities and how they were billions of dollars to build a fabrication facility. The same thing applies to data centers. They're billions of dollars worth of investment. And so anything that we can save and optimize to make sure we're not building new data centers, one, helps with the environmental impact, but it also helps us in being able to maintain what we're doing. But I think as we go forward, some of the requirements are going to start changing on optics. And I think this is one of the aspects that people are kind of missing. You know, why were faceplate pluggable optics so popular? Well, you know, originally, as Bob was alluding to, you know, there was a power problem. But it started to become an operational thing, right? Oh, the optics have failed. I pull it out. I throw a new one in. Oh, awesome. Off I go and I'm up and running again. But that's actually a bad mode to be in, because what happens is it's allowed us to say, okay, we're not going to care so much about the reliability of that because I know I can replace it. But that's going to change, because what's happening now is the ability to get in there and change some of these things, whether it's embedded or whether it's co-packaged, that changes the ability to get to it. But the other change is the environment. So what's happening now is, if you look at some of these, as people may be aware, Microsoft built a data center that we submerged in the ocean. It's not so easy to send a guy down there to replace pluggable optics. So one of the things that we're going to be looking at is, how do I maintain that, gain better reliability out of my optics? And if I start getting better reliability, does that need for faceplate pluggable still sit there? Can that enable things like co-packaging or onboard optics to take place? Because now I don't need to have to service that. The other aspect is, we are also looking at things like liquid immersion, and people are talking about cryogenic cooling. All these environments change how you use these things, and I think that's one of the areas, as we look going forward, is how do I pull the heat out of these systems? How do I build this so I can maintain a lower power node and drive that down? But as Mark was alluding to, and it's tough. These are kind of research and while still trying to push the ability of the technology edge to make it so that we're not having to build new data centers, and so that we can provide those computational resources closer to where people need them. So it comes down to, do I want to try to put everything into a pluggable form factor and make it a Swiss Army knife for everything? And I think the industry has done that for a long time. We did that with QSFP28. I mean, it really was a Swiss Army knife. We could do everything from our Metro DCI right down to a DAC cable. And that was awesome. We're not seeing that same thing. We're seeing a little bit of QSFP-DD and OSFP, and it gets a little bit tougher when we get into those higher bandwidths. And Mark was alluding to 800 gig and beyond, and those are going to come. We all know that that's eventually going to come, whether it's in the 51.2T or the 100T or 200T generations of switch silicon. When that starts to happen, that Swiss Army knife is not going to necessarily be the best thing. And that's where, as equipment purchasers and stuff, we like to have a toolkit. We like to be able to say, here's another way I can do it. Here's how I can remove the power. Here's how I can deal with a different thermal environment. And those become critical elements as we move forward. So I'm a big supporter of having a toolkit. I think we have that today. We have pluggables, we have onboard optics, and now we're looking at things like co-package optics. But these aren't going to be used everywhere. It's not like one's going to replace the other. There will be use cases for some of these, and we know that. But it is necessary to have that toolkit, because I don't think one solution is going to satisfy the whole market. And that's all I had to say about that. Thanks, Jose.
Okay, thank you very much, Brad. Super interesting presentation, as always. So please, now the epic question. What can you do for them, and what can they do for you?
Well, I think that's always the good question. I think one of the keys is let's, as an industry, look at what's going to really happen. I mean, we know the trends, we know how things are built. Even with co-package, we're hearing two different flavors there right now. People are saying, hey, well, we can use XSR, and others are saying we can use a different type of electrical interface, direct drive or LR plus or something. We need to have that discussion to figure this out. We're focusing a lot on how do we eliminate power, but I'm looking at it as eventually we're going to have a problem where driving copper cables is just not going to work. If I get to 200 gig electrical interfaces, copper cables literally have to start disappearing in my data centers. And so for that transition to happen, how do I make optics fit in there and become that copper replacement? I look at it from personally from an environmental point of view. If you've ever seen a copper mine, they're not very pretty. So how do we get to doing something that's more photonics based, whether it's driving across a PCB or whether it's driving across a backplane or across the ocean?
Okay, thank you very much, Brad. So we have a question from Jim, from GG Genuine. Jim, would you like to?
Thank you. Yes, more of a comment than a question. So I don't think optics became pluggable because of a reliability concern and the need to change them out. I think it was a matter of the Swiss Army knife that Brad showed. So the ability to plug anything into a port. And what has changed moving forward is as the switch matrices got very large and became large Clos equivalents, there's always one stage, it's a fan out where everything connects to everything. It's a very common, consistent connection. So there, you no longer need the Swiss Army knife. You could make something dedicated and that's permanently connected because you know it will never be changed. It has one requirement and it's a permanent connection. So there, now that the hyperscales have these large fan outs in the middle of their switch, you don't need a Swiss Army knife like Brad was saying. Thank you.
Okay, thank you very much, Jim. So any additional comment?
Yeah, good
For
to see you,
Brad?
Jim.
For Brad, for Jim? Okay, so if not, let's go ahead with the program. And it's my great pleasure to introduce you Juan Pedro from Telefonica that will give the next presentation. So, well, you know, Telefonica is the biggest service provider in Spain. So I am super happy, Juan Pedro, that you accepted this invitation. And yes, if you want to share your screen.
Thank you, Anna. Yes. Okay. Can you see my screen?
Yes, very well.
Excellent. So thank you again. Thank you, Jose. Thank you, Anna, for this opportunity to present you some these application scenarios for the new optical pluggables for 5G transport. Here, I'll present you some application scenarios where I think the new pluggables could help an operator as Telefonica to optimize the cost and the investments to face with the traffic increase coming from 5G application and other bandwidth intensive applications. Telefonica, I think, as other operators are experiencing a traffic explosion at the edge of the network. And the first question is, where is the edge of the network? Because this is very important to understand what are also the requirements for the optical transport. The edge is not as close as many people can think. The edge, I think that the point where the traffic injection is expected for gaming, for video transmission, and so on, and this fulfilling the latency requirements is what will, in the level that we call the HL2. This means in data centers and collocated with routers in the biggest cities in each country. For example, cities with a population above 500,000. This means that, for example, in Telefonica network, in countries like Spain, and the network in Germany, in UK, or in Brazil, this means some tens of nodes. Tens of nodes where we're expecting, or where we are already deploying the service edge, gaming, video platforms, and so on. And this is fulfilling the requirements for latency, for example. Then most of the traffic, or most of the traffic explosion is impacting in the regional and the access, let's say the access or metro network. And for regional, we mean networks with typical distances or paths no longer than 1,000 kilometers. So most of the traffic, or most of the investments, will be in for channels, for paths with distances lower than 1,000 kilometers, even considering restoration paths. Important in these networks, in the metro and in the regional, we are deploying photonic meshes with ROADMs, restoration capabilities. Dynamic restoration is key in Telefonica, using GMPLS nowadays and evolving to SDN. And for this, having a network with a photonic mesh with multiple paths, the optical spectrum is not a problem. So, for example, the migration to, for example, 200 gig or 400 gig is mainly motivated by the cost efficiency, because the cost per bit is lower, for example, than for 100 gig. It's not the evolution towards higher speeds, 200, 400 or more, is not motivated by spectrum scarcity. Is motivated by cost efficiency. And in order to also optimize this cost, one of the levers or one of the technical initiatives we are promoting in Telefonica is the optical disaggregation. And I think also the new optical transceivers have a lot to say, or there are lots of motivations to have this optical disaggregation. The idea is to take solutions that are coming from the data center world for data center interconnection. For example, single Q boxes doing optical and packet aggregation, and deploy in the backbone, but keeping the same functionalities in terms of performance, fault management, survivability, resiliency that we have in a normal network from a given vendor. And we manage the idea we can do it using SDN. Using a standard SDN architecture, the right interfaces towards the transceivers, we can, for example, select the power, the wavelength, and so on. So one of the applications is in the metro core. Distance is lower than 1,000 kilometers. Typical rates 200 gig, 400 gig. 400 gig. We do not foresee higher speeds, at least in the midterm, in a time frame of 3 years. I think 200 and 400 would be more than enough, but very important to have these restoration capabilities, automatic provisioning, and so on. And the optical disaggregation would be key in order to minimize the cost. Other application scenarios are in the access, let's say for example, in order to access directly to a 5G site, we typically have fiber rings. And for the new sites, because in 5G we will need an intensive deployment of new sites, we will need more fiber investment. This probably is one of the major costs in the deployment or for 5G evolution. And how can we optimize this cost, and how the new optical transceiver can help us to optimize this cost? First of all, by migrating from rings. For example, typically, currently for the 4G, we have fiber rings with gray interfaces, interconnected different sites, and sharing the bandwidth. With the 5G, we can allocate a dedicated wavelength per site using passive WDM and optical transceivers, color transceivers that are installed in both the 5G site, for example, in the BBU, and in the router that is doing the aggregation in our naming the HL4, so that we can have a dedicated or allocated wavelength or capacity per 5G site. According to that, in this case, we are foreseeing most in the short medium term, most of the transceiver would be just 10 gig, dedicated 10 gig per 5G site, and migrating to 100 gig. Important is the DSP integration in this transceiver, in order to enable, for example, to install a pluggable from one vendor, or a given vendor, in for example, the radio side from any RAN, radio access network vendor, or on the router platform. The typical distances are up to 30 kilometers and up to 10 hops as a reference for the application. For example, Telefonica, we have already started some deployments in this sense. So key is the evolution from the logical from the tree to the star topology, from the ring to the star topology. Another benefit that this is providing to the telco operator, Telefonica and others, is to promote the network sharing. For example, Telefonica can deploy new fiber in a given region. Vodafone can do, for example, a deployment in a complementary region, and we can share wavelengths among us. For example, we can do agreements sharing the capacity in terms of wavelengths, so that each one can deploy their own IP network, their own technology, and using WDM, we can share cost. This is something, for example, we are currently doing for the 4G in different countries, this model of network sharing using wavelengths, and for the 5G would be will be really interesting. Finally, optical and packet integration. The optical and packet integration, I think many years ago, we started to talk about the integration of colored interfaces in the IP routers that never succeed. And one of the reasons Telefonica and other operators, I think, do not deploy this optical and packet integration was because two main drawbacks. The first one was that the integration of the optics in the router was impacting in the port scalability. We couldn't have high density port cards in IP routers when we integrated the optics in the router. And the second one was the multi-vendor interoperability. If we wanted optical and packet integration, we had to buy both IP and optical to the same vendor. Now, hopefully, both problems could be solved, and mainly thanks to the new optical pluggables. It is okay with new optical pluggables also integrating for example, the DSP. We can install the pluggables in high density cards in the IP routers, and avoiding this not losing scalability in the routers. And on the other hand, we can configure this wavelength or the optical parameters using SDN interfaces. In the case of Telefonica, we are using netconf-YANG and OpenConfig models to do that, so that we can configure the transceiver, for example, for the wavelength that we need for the restoration, for the provisioning, or for network optimization. And even having a transponder from one vendor over the optical network of other vendors, so that the multi-vendor operability could be assured. So considering this, for example, that the main drawbacks, the scalability and the interoperability, can be solved using both standard SDN and new pluggables, then is really the time for the optical and packet integration. According to that, for example, Telefonica, we are intensively, actively working in the telecom infra project. There were some boxes, Cassini, there are different boxes doing packet and optical integration with different capacities are being developed. And we have started the trials for the deployment in the network with these technologies. Yes, to conclude my presentation, my message is traffic impact in the edge, mainly for regional and metro networks, distances lower than 1,000 kilometers, mainly 100, 200, and 400 channels. We do not foresee anything more, but very important is the dynamicity, dynamic provisioning and dynamic restoration. We are deploying meshes in order to have multiple paths so that we don't have problems for a spectrum. If we have many paths, many alternatives, we don't need to optimize the optical spectrum. But the key is the cost effectiveness. Optical disaggregation could help us to do it. And other applications are in the 5G, the passive rings migrated to stars, and the network sharing, together with the integration of packet and optical integration motivated by new optical pluggables. Okay, that's all from my side.
Thank you very much, Juan. Muchas gracias. It was fantastic to hear from a service provider that the move to 400G was due to cost per bit and not because of throughput or because of all the ideas that we all have in our mind. I love having Telefonica tell us that. And we have two questions from you in the chat. The first one is coming from Aeponics. Francois, what's on your mind? Francois from Aeponics.
I was muted, no longer am I. So yes. Question to Juan. So should 5G go the way of optical front haul with WDM and go from ring to star topologies, is there an ongoing need for optical uplink redundancy, so-called dual homing?
Okay, thank you. Yeah, we are foreseeing the redundancy in the just in the physical path, but not, for example, in the router. let's imagine that, for example, for the 5G, the number of users per site would be very low. The idea is, okay, and if we have redundancy, dual homing redundancy in terms of, for example, the head ends for each 5G site, the cost could be extremely high. But if we have, for example, a ring configuration, we can have a star, but with two separated paths over the physical structure. And the cost for this would be minimum. So most of the risk, that is the fiber cut, could be solved using a star topology with a redundancy. But typically terminating the connection with in a single IP router, in order not to increase the cost. I hope I answer.
You did a good job answering. I think he looks satisfied. We have another question, Andrew from Signal IA.
Thank you. So it was interesting to see your presentation on coherent at the edge of the network. I think people have a pretty good idea of what the cost is of a 400ZR module. And when you look at a 100 gig coherent pluggable module, the cost is about the same, but obviously for the adoption to be successful, I think the price needs to be a little bit lower. I was wondering if you could talk a little bit about what your price expectations are in this application relative to existing 10 gig solutions, or relative to hyperscale based 400ZR solutions.
Okay. Yeah, I think, for example, as a reference, I think that 200 gig currently, the cost for a 200 gig is pretty similar to 100 gig. Is probably 10% higher 200 gig than 100 gig. And so according to that, I think the cost for 400 gig with respect to 100 gig shouldn't be more than, let's say, 30% in order to be competitive, or in order to have a business case for that. And that's, I think that's important. Also, if we consider that most of the applications, or most of the demands, would be for channels that are with the distances below 1,000 kilometers, through regional networks and so on. So let's say, as a reference, we can say that the 400 gig is the target cost is around 30% is higher than the existing for 100 gig.
We have one more question coming from a beautiful country in Europe, coming from Finland, coming from Modulite. Pekko, what's on your mind?
Yeah, I was wondering, I wanted to ask Juan about this WDM wavelength scheme that the Telefonica sees for 5G front haul. I mean, obviously, I assume that the reuse of the CWDM wavelengths is first thing, but when increasing the channel numbers, I think there are different possible options. So how do you see that?
Yeah,
when expanding from 4 to 8, 12 channels.
No, yeah, I think we are going for DWDM. I think the number of channels is very important. Even if I think even the front haul using, for example, CPRI or eCPRI is foreseen in very limited places. We are not assuming, or at least considering, a widespread deployment of optical front haul using, let's say, or Cloud Run, or using eCPRI. The main target is to provide a connectivity of 10 gig or 100 gig to the BBU in the 5G site. And trying to, the main goal is try to optimize the cost of the routers in the access. And if we want to optimize the cost of the routers, the idea is try to increase the number, the scalability, the number of ports in this router, the number of sites that are connected to this router. The idea is to keeping the routers in the same place we have nowadays. and absorb also the increased number of 5G sites. So the key is the number of wavelengths. We need, if we need dedicated wavelengths per site, we need DWDM. And okay, the front haul or ECPRI is not seen as a top priority. It's not discarded, but it's not the top priority.
Okay.
Juan, thank you very much for being with us today. The R&D of Department of Telefonica is a really important one. They are looking for partnerships, cooperations, collaborations. Juan is here to talk to all of you. I would like to remind you right now that after the meeting, for those of you who sign up for one-to-one meetings, we have arranged separate Zoom rooms for all of you. All you have to do is to stay and we'll arrange it for you. All those of you who are interested in one-to-one meetings, just check your inbox. You got a message from Carlos Lee. Why don't we continue with the program? We go to a company who I love. I'm a Silicon Photonics fan. Who doesn't love Inphi? Thank you, Radha, for being with us this beautiful afternoon here in the Netherlands. The floor and the attention of everyone goes to you. I think we have you muted. We can see the San Francisco beautiful red bridge, but we cannot hear you.
Can you hear me now?
Yes, we can.
All right, all right.
We can see your screens quite clearly. If you go full screen,
and
fantastic. Talk to us. The floor is yours.
Okay, thank you very much. As always, Jose, you are just as animated as I've always known you. Having this meeting open with Mark is always interesting. I'm going to be talking about pluggable modules for coherent optical interconnects. All right. So, technology choices. In data center interconnects, we've been talking about a number of different technology choices here. The view at 100 gig, which is in sort of full deployment, you have the IEEE 802.3 PSM4, CWDM4 under 2 kilometers, LR4 under 10. Between 10 and 100, there are a mixture of coherent and PAM4 directed tech deployments, and anything beyond about 100 kilometers. You have a variety of coherent formats from QPSK to 8 quant to 16. As the distances get larger, beyond, I think Telefonica called it edge, up to 1,000 kilometers, metro and beyond, you have QPSK and 8 quam. I'd like to propose a view at 400 could be a little different with the advent of 400G ZR. The ZR has been adopted at OIF, IEEE as a working group, ITUT has the early adoptions of the ZR for data center interconnects under 120 kilometer links. So there is an evolution from what the data center looked like, say about 3, 4, 5 years ago, to what it could look like this year and the next. Volumes aside, there is a real move to deploy ZR, ZR being a pluggable DCO. So what does a switch pluggable actually looks like? So this is a silicon photonics based 400G ZR coherent module. Looks like any QSFP 28 module, except that this is a QSFP DD. And the DSP in there is an advanced 7-nanometer CMOS process. Internally, it's called Canopus. And we have an advanced silicon photonics from an advanced silicon photonics node from a BiCMOS foundry. It's an 8 by 50 gig in, 25 gig PAM4, and output is a single wavelength, 16 quam. Nominal reach, about 120 kilometers. And if I were to get to my pointer options here. So you have the DSP chip, the silicon photonics, the TIN drivers are external, and you have a tunable laser. Silicon photonics is a highly integrated silicon photonics chip with both a transmit and receiver on a single chip. So a single tunable laser splits between the receiver, and the transmitter. And the split ratio depends on the trade-off between output power and receiver sensitivity. The input light comes in, you have a polarization beam splitter and a rotator. Here, they're all TE, by the way, and the output is polarization beam rotator combiner. And this is a compact single chip architecture. And the performance at C-band for coherent links, bandwidths in excess of 30-some gigahertz, 40 gigahertz. It's not as difficult to make photodetectors with high enough bandwidth. One of the important things about building these silicon photonics chips for C-band coherent communications is that you need a polarization beam splitter combiner technology that has got low loss performance over entire C-band and low loss and high crosstalk. So this has got minus 25 dB crosstalk and probably about a half a dB or so loss. So you need a high-speed Mach-Zehnder photodetector and low-loss, high-speed polarization maintaining components. So that's what's inside that module. So if you were to go down, this is the module performance at 80 kilometers, which seems to be the deployment scenario for single-span optical links. And this is a multi-channel. This has got about 32 channels, maybe a little more. A typical deployment scenario these days, people are talking about 64 channels at 400 gig, giving a fiber capacity of 25.6 terabits per second per fiber pair. And this performance at 80 kilometers is with polarization scrambled, real world conditions, and it's got less than half a dB polarization penalty. And this is actually on a real 400G switch in which we are running traffic right now. So before I end, there was a lot of questions about how far can this go? I was limited to about 3 or 4 slides. There's an entire ZR Plus mode that this chip also has, with a lot of vendors out there have. I'm not professing that this is going to go up to 10,000 kilometers, but in a pluggable form factor, you can probably cover up to about 1,000 or 2,000 kilometers. Imagine a single pluggable form factor that can cover the whole gamut from 2 to about, say, 2,000 or 3,000 kilometers. And that is sort of the promise of 400G ZR, and we are well on our way to shipping the we are shipping these modules in sampling volumes to several customers, and we'll go to general availability end of this year, early next year. Thank you.
Thank you very much, Radha. It was a super interesting presentation, and it seems that you have plenty of challenges for our supply chain in photonics. So, well, what would you say? What do you have?
Yes, this is always an interesting question. The challenges are first in silicon photonics part. The common complaint which people have about silicon photonics is you can demonstrate 1 or you can demonstrate 2, but can you do this in volume? All right, that's the whole goal. Can we produce these things? We make these in 8-inch wafers. Can we produce this in volume? And can you have the performance reliably wafer to wafer that's manufacturable for coherent applications? We have a large number of 100G PAM4 modules in deployment, and that's where we had learned to make these things manufacturable. One is the manufacturability of silicon photonics, but at the same time, manufacturability of high-end drivers and TIAs, as well as 7 nanometer DSP. So right across, if you want to make something that small, consuming anywhere between 15 to 17 watts, thermal and layout and supply chain becomes critical.
Okay, got it. So, well, we have a few companies, well, several companies doing silicon photonics here in this meeting. So I guess they would like to talk to you afterwards. But now we have a question from Wilfred from SUS Micro-Optics. So Wilfred, yes, go ahead, please.
Hi, thank you, Anna, for giving me the word. super interesting, especially the talk from Inphi and from Brad, because I'm more on the component side, so that's why I like this stuff. And so we were talking about thermal management and thermal gradients. It's an interesting point that was raised by Microsoft from my point of view. So how can all these components handle this on a chip level, maybe even? So not maybe on a system level, this usually works, but on a component level, what does that mean for me as a component provider? Thermal gradients or thermal stability? Because Cisco, I think they wanted to do co-package optic at elevated temperature, like 100 or 120 degrees. I mean, we make optics now for the automotive industry. We're getting used to these high temperatures, and this is a different business now. So we know now 120 degrees is pushing it, but it's all feasible, of course. And I just wondered what does it mean for us, for our micro optics or integrated optics? How do these gradients?
So you are asking a very relevant question before Brad jumps in here. So the cooling at module level is one challenge, but cooling at the chip level, because all these chips do not have a uniform thermal distribution, is a bigger challenge. It is something. It is starting to become a challenge at 400G pluggable, and we are starting to look at it. And I would love to see materials, if it's out of SIRS, that would allow us to actually manage the thermal gradient within a chip, as opposed to trying to manage it at the board level, because everybody assumes it's uniform. It's never uniform. So yeah, that's an exciting development.
Okay.
Great, thank you very much. And we have Mark from fibeReality that raised his hand. So Mark.
Yes, thank you. I had a question, actually a couple of questions. When it came to silicon photonics, I'm not sure that anyone who got into the datacom game is making money, whether they're part of another company or not. Certainly, it's been more successful on the telecom side, but it's been kind of hidden as to what the actual costs are in terms of dealing with loss and that kind of thing. But my main question is on the 400ZR. The price of admission now is $1,500 or less, which is substantially lower than what was initially anticipated. Does that mean that Inphi has to necessarily consider going back to just maybe just offering the DSPs for that, or do you have some wiggle room there, given the the price crash, which has kind of happened even before the market has taken off?
The pricing is always sort of dynamic here, Mark. By the way, to answer your the other question, we do offer both. Actually, we have a business model in which we offer the DSP chip as well as make the module. So they're both business models, and we also offer the TIA and driver, but the driver that we use internally is optimized for our silicon photonics. So the business model for Inphi is flexible. So we are not. We like to treat the ZR module as a packaging vehicle, and if somebody were to take the pieces and come up with a more creative package, that'll be just as fine as well.
Okay, thank you very much. Any question or additional comment about this? Well, we have, I saw Johanna from Mintres raised her hand. Please go ahead with your question.
Hi guys. I'm working for Mintres, where we're dealing a lot with thermal management of the chips and also at the hotspots of the chips. So then immediately I wonder, did you guys try to use diamond placed as a heat spreader directly at the hotspots of such a thermal chips?
We haven't gone that far yet. We don't usually disclose all the things we do, but that is in some part of my life, we had used industrial diamond before people get any ideas.
Yes, correct.
that's a very interesting idea. No, we are not using it. Not for any other reason except cost. From the last time I looked at it, if they had come down in cost favorably, we might end up considering it as well.
But
So
Joanna,
what
I'm
is-
sure it is not the first time that people answer that to you, right, Joanna? How do you answer that when people say, "Oh, diamonds are too expensive"? How did you answer that?
Well, that's exactly wrong answer, because we're talking about very small piece of synthetic diamond.
Yes.
So we're not using like big chunk of 1 by 1 centimeter. We're using, for instance, 1 by 1 millimeter, and that's already quite a big piece. So if you can put that kind of piece or even smaller chip into the hotspot, then you're actually helping to remove the heat generated over there. And of course, then you have some additional thermal package that helps to extract that. And diamond is actually the fastest extractor of the heat and the most efficient here. So then the price could be even $10 per piece. So that depends actually really on the size of such a synthetic diamond, where it's placed also.
Yeah, your point's exactly right. It's not a large piece. So the way commercially we move is we go from copper-filled vias to gold, graphite tapes, and then to diamond. We might be well on our way to using it. And your point is absolutely right. It's a very small piece of what we call industrial diamond or synthetic diamond.
Right.
We are very excited of what Mintres is trying to do to bring. They are already very active, bringing integrated photonics with diamond and other applications. We need to push the telecom market. I fully agree with Joanna. It is not a cost, definitely not a cost reason. Yeah. I'm going to read a question from the YouTube channel all the way to my friend Radha. I'm going to read a question from a fantastic company in Florida called Lightpath. Douglas Aguiar is wondering, in the BER versus OSNR plot that was shown, you had a prefect for the bit rate about 1 exponential -3, even with 30 dB of OSNR. And he wonders, what are the impacts of noise floor have on the operation of the links? Is it more difficult to compute link margins, for example?
No. What we do is the area floor is an indication of how some things are put together inside the system. But what area floor? I understand your point. The question is okay. This is a much longer answer than I thought. The bit error rate correction limit is 1e - 2. So if we were to look at the post-FEC system, you'll find that it's completely false. It completely corrects itself at 1e - 2. This floor, about 1e - 3 floor, these are the initial modules they've built. The new ones that we have do quite a bit more, quite a bit better in our area floors, but they don't go to like 10e - 4 or 10e - 5. But they straddle between -3 and -4.
I think that's a good answer. That's a good answer.
That's a better answer than trying to explain the BER.
I can make introductions. You two are really nice people, and you're both my friends. I would like to introduce you. We're going to move to the next presentation. We're going to go now to the beautiful world of indium phosphide. We have now 2 booming companies, one on the United States, one on the beautiful Netherlands. We go first to Infinera. Gloria, muchas gracias por estar aquí. Thank you very much for being with us this beautiful afternoon, morning for you in Pacific time. The floor and the attention of everyone es para ti.
Thank you, Jose. Let me navigate through here. Can you see my screen?
Not yet. Almost here. Is now through the Atlantic, and it's here. Yes.
Okay. Well, you must be. We must need to use more Infinera networks. So, good morning and good afternoon. My name is Gloria Hoefler, and I will be presenting on the integration competencies that we've developed at Infinera to commercialize our products for optical network solutions. So, we believe that these technologies are relevant to reach, COBO objectives and pluggable transceivers. And as many of you already know, we're an optical network solution company, and our approach to developing optical networks has been a high degree of vertical integration. So we are organized to leverage the synergies of integration across the group. So the group that I'm part of, the Optical Innovation Center, we develop ASICs, DSP, analog electronic designs, highly customized drivers for the PICs and the modules. We also develop the modules, but we also have manufacturing lines for the packaging and the optical chip fabrication. And over the years, we've developed competencies in RF interconnects, which are necessary to meet the demands for higher and higher data rates. We believe that these technologies need to come together to understand the trade-offs and optimize the system-level designs. We've heard about crosstalks, thermal and electrical, and so this is all really important to look at in the context of co-designing. So ultimately, the result of a high performance and more reliable optical engine really comes from merging and looking at all these technologies together. So so these competencies and integrated approach is what we believe is relevant for the objectives of performance and pluggable transceivers as well. So today I will share an example of our i6 engine and show how vertical integration enables leading system performance. We drive innovative solutions, so I will also highlight coherent point-to-point and optical networking in our foundry services. So Infinera has pioneered the use of large-scale photonic integration for multi-channel transceivers since 2004. And over multiple generations of coherent optics, our PICs have become much more complex, requiring intimate integration with electronics to meet the speed requirements and signal integrity. So let me first start out by describing the architecture of our latest module, which is our 1.6 terabit module. It's a two-channel PIC, each operating at 800 gigabits per lambda. So let me walk you through some of the details of the indium phosphide PIC. First, I'd like to note that this is RX and TX functions integrated on one same chip. Each of the transmitter and receiver channels includes its own independent, widely tunable laser with line widths less than 50 kilohertz. And this is, so basically a total of 4 lasers. This allows for independent tuning of the RX and the TX channel and network configuration and an uncompromising power. We also have 2 sets of dual polarization IQ modulators and 2 sets of dual polarization coherent receivers. So for system advantages, and because we can do that in indium phosphide also, we amplify and control by using power on chip SOAs, and these are monolithically integrated at the output of each polarization stream. To support the high electro-optic bandwidth, the PICs had a matching high density 2-channel SIGI ASIC, 180 nanometer with 4 modulator drivers and 4 transmission impedance amplifiers. We deploy fiber V-groove arrays and arrays of polarization beam combiners to couple the light out of the fiber. So due to the high level of integration, this transceiver requires significantly less assembly and less alignments than components needed for even a single channel transceiver using discrete functional components. So I'm playing around with my controls here. I apologize. Both the PIC and the ASICs are co-packaged with free space optics and polarization control elements, and have demonstrated bandwidth in excess of 55 gigahertz and a record of 100 gigabytes using 64 QAM operation. And this was demonstrated a few years ago at ECOC. We have productized this now into an 800 gigabits per lambda transceiver, which is assembled into a DCA optical module, a DCO. with our latest 800 gigabit or 800G DSP and the support electronics. So the DSP ASIC incorporates also digital Nyquist subcarrier generation, probabilistic constellation shaping, cross-channel coding via multiple dimensional modulations, and channel forward error correction. So we have already completed many live trials and various fiber types, closing up to 970 kilometer links at 800G. What I'm showing here is an example of the Whitestream live demonstration. You may have seen some of our press release on this. And you can see that the receiver constellation is nice and clear. We divide the spectrum into subcarriers, and we have also demonstrated 800 gigabits that transition across 1,000 kilometer link using this DCO. So this product really brings out the benefits of vertical integration from the monolithic PIC that is hybridly integrated with high density 2-channel ASICs and co-packaged with free space optics up to the assembly of the DSP and into a DCO. Now, the commercial line that offers or that builds this PIC has also been now open to foundry service and foundry capability, and we did that by partnering with AIM Photonics to develop a PDK capability that was completed very much like our commercial products, using a very system-centric approach. The platform is designed with electronics and packaging in mind, so providing users a turnkey access in reference designs, both for the functions as well as for the electronics. So it allows users to really focus on the prototype and a path to commercialization. We did this, also by developing design automation tools for simulation and layout, and this minimizes transition to manufacturing. We've worked very closely with simulation vendors to generate compact models that are derived from commercial baselines. If you're interested to hear more about the details of what we are doing in this area, we're going to be having a talk tomorrow at 8 a.m. PDT, Pacific Standard Time. It's an OSA webinar jointly hosted with VPI Photonics. So welcome to hear some of what the things that we're doing there for the foundry capability. I just want to say that along with what we're doing there, we have some ideas on how to transform network from point to multiple point, improving operational efficiency, cutting the number of transceivers in half, and eliminating other inefficiencies. And as you see on this graph, we have a hub where all the data goes onto the aggregation point and then connects through a 2N transceiver coherently to the edge of the network and then onto off-key to the users. However, if the aggregation point could be if we could use a pluggable form factor gadget like an XR optics is what we're calling it, with digital subcarrier technology that transmits from one point to many, the network can be transitioned from 2N to 2N plus and offering multiple advantages. So to sum it up, a multi-point transceiver in pluggable format that enables 2x reduction in the number of transceivers and simplifies the network. And we have announced several partnerships in this area. And along with all the work that I presented, we're open to discussions and collaborations. I hope that I have shown technical competencies that need to come together to develop these leading edge performance through holistic co-design and monolithic integration. So just want to point out that the level of integration that is shown here is novel in that all the optical functions needed for coherent transmission and detection are optimized and monolithically entered or embedded in a single indium phosphide chip that reduces the size and the complexity of the packaging and assembly. And holistic integration, in our view, is really critical. It's fundamental for more innovation, but it's really critical because it enables us to understand the trade-offs and reduce the, optimize, the areas that are critical and maintain a high level of signal integrity. Thank you.
Thank you very much, Gloria. It was a great presentation because you presented different ways of collaborating with our members, well, with the people in this room. So, well, maybe you can summarize what kind of challenges would you like our members to help you with?
Sure. So our challenges are always in the area of, thermal crosstalk, RF and RF integrity. So thermal and electrical crosstalk are usually challenges that we're faced with. In the on the foundry side, some of the challenges are in the area of interoperability of the tools, of the EDA tools, and those are just some of the challenges that we face when we develop these products.
Okay, so maybe it's a good, well, yes, because Greg from ficonTec had a comment related to the packaging, well, right, yes, related to the packaging and assembly. So Greg, if you want. And also I think you have a...
Hi, thank you, Ahmad.
Yes.
No, I don't actually have a slide ready on this. It was more like spontaneous.
Okay, so well, just a comment about what is ficonTec doing and how can you help in packaging?
We're interested in the packaging technology area. This is, if you look at co-packaging as a set of individual processes, it's probably nothing that we have not seen already in the sum of our activities. We are, of course, very interested in learning about where manufacturability of these units is on the timeline for the developers. We've heard about cost concerns, we've heard about issues. These are all, of course, tied deeply together with ability and information that we'd be keen to hear about.
Okay, thank you very much, Greg. And also we have a question from Wilfred from SUS Micro-Optics. Do you want to go ahead with the question, Wilfred?
Yeah, I just wondered if the reason why you opened up you kind of opened up your foundry with a PDK. Are you looking for other applications besides data and telecom, besides these classical applications? Do you see other markets that are growing or emerging, or just curious?
No, it's a good question. Yes, we are certainly open to other applications. In fact, where we offer, our expertise is not. It's obviously in the telecom area, but this expertise is transferable, at least on the monolithic integration to other areas like sensors. We see applications in defense as well as LiDAR for high volume.
Here we go. Yeah. I figured LiDAR or medical, but LiDAR is probably. I'm very curious about LiDAR because this is coming and going, and I don't know. How do you see the future of LiDAR in this context, in this optical? That would be interesting to know.
I think the last time I saw, there was probably over 100 companies that were trying to do LiDAR. So I think there's a lot of different approaches, but I think at the end of the day, a lot of the LiDAR approaches that I have seen require high power lasers, and that typically requires some level of integration with indium phosphide. So we see that as an up and coming.
Okay. Thank you.
Okay, and we have another question for you, Gloria, from Chris from BPI Photonics. Chris, would you like to make the question?
Yeah, hi, Gloria.
Hi,
yeah,
Chris.
This is Chris from BPI. I just have one question. I'm curious, in terms of your Open Foundry, what type of support does Infinera provide to your customers to get their ideas fabricated?
That's a good question, Chris. Thanks. Actually, Infinera works very closely with the users. What we've found in the past from the founder runs that we have done is that a lot of the users that come to us really are system level users, and so they welcome our support in the way of integrating the PIC into their system, and we work closely with them in terms of providing the tools for the simulations as well well as the controls that are necessary, not just at the system level, but also for the assembly. So a lot of times, control loops that are required for managing the PIC in the system require integration of components that they have not thought through, and so that's I think one of the areas where we add value to our users.
Okay, and last thing, I would like to introduce you a company, for maybe, why not, for a potential collaboration. So I can see here Gravi from Sabic. Hello, Gravi, would you like to introduce your company? And maybe, if I am not wrong again, you have a slide to show to us?
Thank you, Anna. No, I can do without slides. No, Sabic, indeed, we make plastics that are used for the optical elements in optical transceivers. So both from the transmitting as the receiving side, and they're used because they're optically transparent, but also have high dimensional stability at different temperatures. And we're working on actually new plastics for onboard optics that have even higher heat resistance, that can withstand reflow soldering or SMT, as we heard earlier. And also even the polymers with a lower thermal expansion coefficient, close to the substrate that these lenses are glued on. So close to 20 ppm. And actually, we're looking for partners in the value chain to work with us to evaluate those materials. And we can offer is obviously global research centers where we can do micromolding for optical elements. We have mold flow analysis to help you moving away maybe from glass or thermoset to plastics. And we have a global network for micromolders.
Yeah, indeed. After the presentation from Effect Photonics, I would like to come back to Gloria. I would like to come back to Radha and understand a bit what are the needs for optics and micro optics for the packaging of transceivers, because we have huge, amazing technologies right now in EPIC, and this is a huge potential market for them. Back to Anna.
Well, no, that's it. If there are no more comments or questions for Gloria, I think that we can move ahead with the program. And well, talking about indium phosphide, it's my pleasure to introduce you Tim from Effect Photonics. So, Tim, if you want to share your screen.
Yes, thank you very much. Let me see if I can share the screen. Hold on. There we go. You should be seeing the screen now, and also let me get the pointer options going. So, separately from sort of my esteemed colleagues in this group, I feel it's necessary to explain a little bit about what Effect is and what we do and where we come from. So I've taken Carlos and Jose's remit to heart. So the slides are in the format of who are we, what are we doing, and what are we looking for. So let's take it away, right? So you should be able now to see the next slide. Yeah. So Effect Photonics, basically we are a transceiver vendor for DWDM transceivers, and we're basing all of our module designs on our core technology, which is monolithic integration of indium phosphide. So what are we doing? We're integrating lasers, modulators, photodetectors, splitters, but also network filter elements like AWGs in our designs. So we integrate all of the optical functionalities into one chip, into one indium phosphide wafer. We do that monolithically, and that really allows us to scale into applications where the power and quality of high quality indium phosphide was not affordable yet. So we're really taking the high performance that indium phosphide brings, putting all of that on one wafer and then scaling that so that we can use it at metro access and at some point also even for data center applications. We combine that technology with the capability of non-hermetic optical packaging, which is a key cost driver for pluggable modules. And that together really brings a couple of very interesting benefits for our modules onto the market. So on the right, we see one of our early chips. This is an example of how much we integrated. I think this must have been in 2016. So this is 10 tunable lasers that you see here, together with a AWG combiner, optical amplification, wavelength locking, and many other functions on one die. So we started in 2010 as a spin-out out of Eindhoven University, but here in Eindhoven in the Netherlands has been a strong background and heritage in diode lasers and integrated optics, tracing all the way back to Philips Optoelectronics. We now have about 170 employees over 3 sites in the UK, in the Netherlands, but also in Taiwan. I think one of the interesting points is that we are doing this indium phosphide technology fully fabless. So we own and we run our own PDK, process development, tool development, epitaxial design, but we run that through commercial volume foundries. So, okay, that's who we are. Now, what do we see as a next-gen vision? So market segments for pluggable modules. Now, I apologize, this is a gross oversimplification for how complicated the internet really is. But in a nutshell, we're seeing 4 different parts of the market. Long haul, metro and DCI, access and data center internet. There's obviously ultra long haul, and on the top left corner, you would see also things like onboard optics or maybe even chiplets. But in a nutshell, in long haul, you're requested to transmit data over thousands of kilometers. So it may be 1,000 or 2,000 or maybe up to 8,000. And as a company for a particular product, you may be able to sell 10,000 of those modules a year. Yeah, maybe it's 10,000, maybe it's 25,000, maybe it's 50,000. When you go into a successful metro and DCI application, we're really now talking about hundreds of kilometers, 300, 500. We've heard discussions today about where the edge really stops. But most of the applications and most of the module designs really top out at maybe several 100K modules a year. Now, there's obviously aggregate volume, and there may be modules which are second source, but roughly speaking, that's correct. Now, if you bridge up to the top left, when we're talking about access, that may be 10 kilometer, 20 kilometers, 30 kilometers, but most of the applications are in the multiple millions a year. So every time we go up, we drop a factor of 10 in the transmission distance, but we increase the volume that is needed to adequately fill that part of the market by the same amount. So that's quite an interesting trend. Now, if you really want to be a high volume data center player, yeah, we're really talking about 10, 20, 30 million pieces a year. So the types of manufacturing, the types of technology choices that you use really scale for these business cases. Now, what we're seeing is that coherent is obviously a very powerful transmission technology, brings many benefits in signal to noise ratio, link distance, and for some type of very long distance applications, it really is the only way to get your data to the other side of the fiber. Now, that means that up until now in 2020, and probably also for the next 3 to 5 years to come, coherent is going to dominate, long haul, ultra long haul, metro, and DCI. I mean, that's in line with what we've seen today during the presentations. And we believe that almost all of the links above arbitrarily 80, maybe even 40 kilometers will go to coherent in some way. So what would it take to really move coherent into almost every part of fiber optic communication? Because now direct detect really is dominating the data center, the Ethernet, and the access markets, but what would it take to go to the next step? So what we believe is it will take really a quantum leap, a really next generation coherent to fully encapsulate almost all of the fiber optic links and bring coherent technology to that. So you would need low power consumption, low cost, because you have to make it in massive volumes, has to be high performance, because the data rates of every single link length are going up. They're going from 1G, 10G, 100G, 400G. We've been talking about 800 and beyond. And that means that for an arbitrary link length, if you want to go from 800 to 1.2 terabit, you're going to hit the fundamental issue that coherent will be the only way to get your data to the other side. So coherent will have to move up this diagonal and will need to move 1 or 2 magnitudes in production volume. So what does that take? Well, obviously it needs scalable optics and it needs scalable electronics. So in the format that Jose has asked, let's first look at which part of that puzzle we believe we have. So this is actually sort of a world first, and happy to give the team at EPIC here the scoop. So in the long tradition of indium phosphide picks on a finger, you may have seen the first part at the first part of this presentation that traces all the way back, I believe, to Agility and or JDSU for the first tunable laser on a very well manicured finger. We are continuing that noble tradition here with our latest addition to that technology. So this is our single die monolithic multi-rate indium phosphide pick, and based on this technology, you can see it here. It's on here. It's on the finger. And what's in it? It has the coherent receiver. It has the monolithic sub 100 kilohertz full band ITLA. It has modulators, but also it has optical amplification throughout, also integrated wavelength clocking and RF termination. The interesting thing is this chip brings the full benefits that also Gloria has discussed of indium phosphide integration, high-speed modulators. We have also 50 or 53 gigahertz modulator bandwidth and similar PDs. We have high-power ITLA, and it's all monolithic, low loss on the chip. That means that you can really cover a wide range of applications. We can configure this single chip into sort of a low power, short range mode, but also a high OSNR long distance mode, and almost anything in between. We can hook it up to 100G and 600G electronics and really use this chip design, which we have invested the last decade of process technology development into, and really make a massive range of different modules happen. Now, the optics package that we've designed around it, because we've put everything in the chip, the optics package actually becomes, I would almost say, deceptively simple. So we can fit it into sort of the smallest, but also the largest module. So this optical package, we can fit into a QSFP28, a QSFP-DD, but we can also easily put it into the incumbent standards like CFP2 and CFP right now. So we really believe that to get to 1 million coherent anything, you really need to have a monolithic semiconductor technology and just run lots and lots and lots of wafers. That's the only way we believe we can get to 1 million or 10 million coherent modules being sold. So we're working on this, right? So this is the first prototype. It's sort of a global scoop. We've put a press release out early this year that we were working on this chip, and now it's finally here and the real work starts. But what do we need? So if we go to the next slide, and I've happily taken some of the people's products in this group and put them on the slide. So really, to get coherent to work through all ranges and all volume amounts, we believe that we have the optics technology that can scale very well on terms of power and link distance, but also with volume. But it's quite obvious that pairing that with what's in a sense long-haul DSPs, even if they're very capable and of the 7 nanometer type that we're currently using, really doesn't get us to the point where we can really say, okay, it's going to be 1 million or 5 million or 10 million that's being used in all of the access networks and all of the data center. And obviously this will be a couple of years out, right? This will be 2025, 2026 and onwards. So really what we are looking for as Effect Photonics, where will the next super high volume, next generation electronics, both on the signal processing, but also on the electronics, where will that come from? And which partners are really going to jump into this part of the market to support the optics that are now scaling towards that part of the market. So I tried to encapsulate the narrative a little bit, Jose, but that really is in a nutshell our presentation.
Even though we know each other for a long time, I think it's like 15 years. I would like first of all to say congratulations. You are one of the founders of Effect Photonics. Yes. Last summer you became the CTO. I love when great things happen to great people, and you are making a big difference on the European ecosystem, playing with the big guys. And I'm amazed by what you have achieved in the last 10 years. So I would like Effect Photonics is the jewel
Thank you
of
very
the
much.
EPIC.
Thank you
One
very much.
thing that I love with Effect Photonics in EPIC, you're always here looking for partnerships, looking for potential people that can help you. So I would like to, as I promised in the previous presentation, I would like to go back to the three companies, Inphi, Infinera, and Effect Photonics, and ask you two questions. The first one, need for micro optics in packaging. The second one, assembly and packaging needs in the supply chain. And I'm going to start with the CTO of Effect Photonics, Mr. Tim.
Yeah, thank you. So really what we are looking for is, every time you go into making something 10 times as much as you're used to making it before, almost all of the supporting technologies have to scale up to the next level, right? So it's all well and good to handcraft under a microscope your first gold box packages with manual assembly when you're making 1,000 a year. That doesn't really scale when you're making 10,000 a month or maybe 100,000 a month. So from packaging technologies that really scale to, for example, a global network of contract manufacturers, or from, as a sidebar, one of the reasons why the DSPs are now so expensive is that taping out the 7 nanometer DSP for a 50,000 or 100,000 a year run rate really is not a whole lot of silicon to be selling to offset the development costs. So in optics and telecommunications, we're really still using a high amount of very dedicated and in terms of silicon, still relatively low volume components to support the TIAs, the drivers, signal processors, but also things like custom ceramics. And to really make a massive impact with the telecommunications and datacoms industry on sort of the global supply chain of PCBs, metalworks, housing, and silicon, we really have to graduate to the next step up.
So when the EPIC members see a slide like this, they get really happy because they see a chip there, and you talk about the optical input outputs, you talk about the RF input outputs, and you see a lot of active components packaged in a reliable way. Could you share with us maybe 1-2 challenges on optics, fibers, packaging that, maybe the people from EPIC can help you, not for this product because it's already fully mature, manufactured, and it can be packaged in any form factor, but maybe for the 3.0 generation?
So, what you see on the chip here is, you integrate more and more functionality into a single chip, which also means that you have to have more and more electrical inputs in and out. So, the arrows don't really do it justice. There's RF in and RF out, but actually it's, a couple of hundred contacts that need to go in and out. And, up until now, wire bonding has been the idea of choice. I know that Infinera has been doing very well in flip chipping, but I think getting to the maturity of flip chipping that electronics has for optics packaging and really making that standard rather than the exception is something that we would really be interested in collaborating with.
Excellent. You're going to get a lot of emails after this. Remember, any company that wants to be introduced, I will make an introduction, an email introduction. Going to go now to Gloria. Infinera, same question goes to you. A couple of challenges, room for a collaboration in companies on packaging, assembly, and micro optics. We have you muted and we really want to hear you. Yes.
Okay. Okay. Thank you for unmuting me. I think Tim has really highlighted already the key areas for collaboration. I think it's important to note that there are emergent applications in indium phosphide beyond datacom and telecom. So in the sensor area, like LiDAR, and there, the challenge in the packaging would be quite different. You have environments that are very harsh, and the cost has to be also competitive with the application. So finding, either optics or free space optics, whatever the solution is, that is reliable under the environment of operation. Probably RF is not as important in that sense, but the optics are.
Gloria, in the EPIC family, we have companies that can do wafer level micro optics, and it's a big thing. We have companies like aextris, SUS, Nanoscribe. I apologize because I could talk for I could mention so many. Do you see a challenge in the need of low cost volume production wafer level micro optics for the co-package optics?
So let's just take LiDAR, for example, because that's one of the things that I had mentioned earlier. In that area, not only do you have very stringent requirements on the environment, operation environment, very high temperatures, you also have very high powers. So the packaging needs to be low cost, but it also needs to be competitive with high power applications. So you don't want to spend a lot of money on your chip making the photons and then losing them in the coupling process. So that, I think that is the challenge there, the thermal and optical coupling, if you want to.
The same to you, Gloria. Be prepared, because I'm going to introduce a lot of potential collaborators from the US, from Europe, from China, from all over the world that they want to work with you. And I really also want to work with you, Gloria. And I go to Radha, I go to Inphi. Also, the same question goes to you. A couple of challenges on the micro optics, on the wafer level optics, on the fiber, on the packaging for Inphi.
I actually sent just sent a private chat to the gentleman from Sabic. Yes, we are interested in high temperature lens elements. So yeah, we'd like to take a look at that.
Fantastic. This is when the magic happens at Epic. I hope.
I didn't. There wasn't a slide, but you had briefly mentioned about packaging for really high temperature applications. Ours is probably not. I don't know how high we're going to go, but anything in the range of 80 to 120 would be of interest.
Gabri, I think that's something that you definitely can do.
Yeah, that's not a problem. We can go all the way up to 260 for reflow soldering. Yes.
Oh, yes. Operational temperature and there's assembly. Assembly 260 would be good. Yeah, 260 is about the number. It's it's one of those leadless tin-based solder reflows. 260 would be about.
I continue looking for partnerships. I'm gonna go to Belgium. I'm gonna go to Skylane Optics. Philippe, how are you doing today?
Fine, and you?
I'm looking for friendships and collaborations. You make fantastic transceivers. What kind of cooperations you see in the field of packaging, assembly, micro optics, etc.?
No, we work on Interoptics. We try to interoperable optics, and I like to listen to all the presentation. As you know, a few years ago there was only a few manufacturers of DSP in the market, and today there are more than 7 DSP manufacturers in the world. And as you know, everybody is somewhere proprietary. That means my question that everybody wants to work together, everybody wants to reduce the cost of the high-speed optics, but everybody is making his own DSP. Then I don't understand very well.
Who wants to address that? Why is everybody making their own electronics, their own DSP? Tim, you're smiling. I think you have a vision for that, because we discussed this over a decade ago when we were together at TUI in Doven. What is the reason behind everybody going all the way on making their own electronics?
I'm not super sure if I'm perfectly qualified to answer that. I think there are better colleagues in this group as well. But what we are seeing is that, especially when you are trying to make transceivers and you're working together with system integrators, how to differentiate what you're offering into the market is very important. And the DSP is a very strong ability to differentiate your offering, but that almost goes directly against what the market needs, which is the same modules which work together, and which are easy to buy and cheap. So a large part of it has to do with sort of supplier and demand dynamics. That doesn't explain anything, but yeah, I mean, even from a module developer like ourselves, the more we can find a DSP that works for most of our cases, the more we can drive down the semiconductor volume curve with our optics, and likewise with all of the electronics to follow. Yeah.
I do believe that there is just not a generic solution for everyone. It's not available in the market. If it was, you would be the first one. All of you would be the first one to get it. Philippe, I'm looking forward to help you more with more potential partnerships. Skylane is a fantastic company, but we have to move on because I want to finish on time. And I want to go to one key company in the ecosystem. Vipul is a great friend of Epic, and Cisco is very important for us. Thank you very much, Vipul, for being with us this beautiful afternoon.
Hey, good morning and good afternoon, everybody. Vipul Patel from Cisco, I prepared this presentation in a very short notice. So I'm mainly going to touch upon some of the challenges that the next generation optics will face from product development point of view. And with that, if you can go to the next slide, please.
Sorry, almost done. Okay.
No problem.
No problem at all. Don't worry.
Now?
Yes.
Okay,
no,
now.
you're sharing the wrong screen again.
I think while you're changing a slide, let me give you a little history of silicon photonics also. In 87, around mid 80s, Richard Soref from Air Force developed some of the initial concepts. Unfortunately, no SOI was available at that time, so it was based on a doped silicon waveguide, very high loss. Real work on silicon photonics started in early 2000, and fortunately or unfortunately, I got stuck with the field since very early days of silicon photonics. What is possible with silicon photonics, or what has been demonstrated so far? Baud rates up to 50 gigabaud are already there in the products now. Going to
the screen is perfectly working. Vipul, you can proceed.
Yes, it is working. It is
yes.
working. Thank you. Yes. So going to 100 gigabaud in silicon photonics, from at least technical point of view, it's achievable. One of the promise of silicon photonics is that it allows a massive parallelism, that you can do optics now on a silicon. So you can add as many fiber links as you want. And if you look at it, one of our, a company that we acquired, Luxtera, has done PSM4. Lightwire, when we acquired, we did also 10 by 10 CPAC module at that time. WDM, DWDM, Intel has done CWDM4 based products. We from Lightwire team also did a DWDM product that was a CPAC 100 gig LR4. Modulation, PAM4 modulation is very easily achievable, and we have at OFC 2019 demonstrated a single lambda PAM4 for 100 gig, 50 gigabaud. And going to PAM8 also is possible. On a TX side, its RX becomes more challenging. Coherent, you heard already from Inphi. Acacia, that we are in process of acquiring also in that field, and Nokia also recently acquired Elnion, that also is in that space. And now one of the discussion that happens or where silicon photonics comes up very often is in-package optics or a co-package optics or a COBO. So with that, if you go to the next slide, please. Okay. So if you look at the history of silicon photonics, again, as I mentioned, I have been working in it for 2 decades now. Lots of people started at that point. And you heard from other players in this field also that majority of the company, it's a multi-year of R&D before a product can be realized. So why is that? One of the major challenge is that it's all co-designed. You cannot invent things in a silo in silicon photonics side. Just to give you an example, the photonic IC that is in the blue here, the 2 main components there are modulator and a photodetector. One of for transmit, one of them is for receive, and then you have all the waveguides for out signals and everything else. And every company that is in silicon photonics right now has a individual PDK of their own and their own fab engagement. So no 2 companies use identical fab process or have identical PDK elements. So that doesn't mean that you cannot achieve. Almost every company can achieve the functionality that is needed once the light is in the silicon. The biggest challenge is how to couple fibers to that silicon photonic IC and how to get the laser light in while keeping the thermal, electrical, and all the mechanical aspects intact. And that seems to be a major challenge. Now that is still for for pluggable optics, that's still relatively simple because you are not constrained with the packaging that needs to be done for a board level packaging or a SMT level, the more standard electronic packaging. You can customize your packaging. But when you take this situation and go closer to the IP or in-package optics, or also co-package optics, what is known as, now you are putting optics close to a very large scale heater. In that world, they don't talk about power dissipation in watts, but in hundreds of watts and sometimes in kilowatts, when you especially talk about a 50 terabit or 100 terabit systems. So now optics, for example, laser will fall off the cliff if you have to, go beyond 90 centigrade temperature there. Same thing, we talked about epoxies and everything else. So a lot of those things, the optical component, reflowable compatible optical components, epoxies, a lot of those things plays a major role. And you need to know those constraints when you invest in your photonic IC platform. So that's what makes it very challenging. So if you look at it, the industry-wise challenge, and one of the good thing that EPIC is doing is bringing everybody together in a consortium way. And so common roadmaps and common challenges can be identified and people can work collaboratively. So if you go to the next slide, please. So what are the main challenges? As I mentioned, there is no standardization here. Each company has its own PDK, own process flow. Same thing applies to light sources. That's a very long and expensive development cycles for lasers. And these lasers are also custom in many cases, designed for a very specific silicon photonics. Another item that was discussed here was on a DSP side. So why there are no, why there are 7 companies and why there is no economy of scale? Because everybody, ASIC has 2 components. One of them is the SerDes and CDR, and the other side. And that can be probably standardized, but the interface to silicon photonic IC is always custom. And at least unless the PDKs become common, right, that part, the TIA interface, the modulator driver interface, and sense and control interfaces has to be custom. Now, doing any customization on a 7 nanometer node, we all know how expensive it is. So that's where the economy of scale or the cost margin reduction, right, is challenging in this field. Same thing happens to OSAT and especially for either wire bondable or chip on wafer assemblies. But again, everybody is a low volume custom flow in a high volume facility. And on assembly side also, there are multiple models that at least we have still in the industry. Lots of people have their own CMs, contract manufacturers. There are some joint development type of things that we have seen also in the industry. But again, there is no standardization even from equipment making point of view, and that is a must. So in summary, what I can say is that supply chain still for silicon photonics in infancy, and we have to work collectively in many areas to overcome some of these things, and standardization has to take place if we truly want to realize the potential of silicon photonics, which when you go to very high density optics, or when you have to make an optics that is a higher temperature compatible, that will become the need of the hour. So with that, I'd like to summarize this article, summarize this presentation. If you can go to the next slide, please. So it is identified silicon photonics is one of the key enabler for scaling, both the massive scale data centers as well as the coherent side. It's fast growth from aggregated growth point of view. The heterogeneous integration, meaning that wire bond solutions are disappearing or going away, and people are going more and more towards doing a flip chip type of packaging between the electrical ICs and the optical ICs. There is very strong momentum. Every company has a roadmap. As a Cisco, we presented our roadmap to our investors in Wall Street. And in fact, if you do a search with one silicon strategy of Cisco, I think it was present last November or December. And even in our quarterly reports, optics has been identified as one of the key growth area for and a focus area for Cisco. But again, in order for us to realize that new silicon photonic ecosystem has to be developed, and any company here who has a newer technology that can help leapfrog that and want to make a presentation to Cisco, you guys can reach me out. And the focus also for long-term development point of view. So one of the thing that that was mentioned in previously, right? That you have to intercept the market at the right point also. As I mentioned, these are very, very long development cycles. So the investment you make today has to meet a market intercept point, has to be well defined, and that can be 5 to 7 years down the road. So co-packaging and optics probably fall into that category, that it's an imminent, it is the need of the hour, and people have to start thinking seriously about that because this is very, very long development cycle. So if you don't make right bets, then it's very difficult to catch up. With that, if you have any questions, I'm more than happy to answer.
Thank you very much, Vipul. It's always a pleasure to have you and to have Cisco in our meetings. And well, you already answered the questions because you presented, yes. In this slide, we can see several challenges and a lot of room for collaboration with our members. So maybe we can focus here on your co-design and well, your needs in design, because we have here in the room a company doing design tools, Optiwave. Would you like, maybe Radha, would you like to comment? I think you have a slide, right, to show you about what are the tools that you offer?
Yes, hi everyone, and let me share the screen here. Okay.
Okay, so if you can go to presentation mode, well, if not, it's okay.
Yeah. Okay, yeah, here we go. And one more slide here. Okay, so yeah, so just quickly to go through what Optiwave offers as a system tool, which can help system companies or designers, manufacturers of these transceivers, is the wide range of components and models which can be implemented in the software, which this software would be called OptiSystem simulation tool, and we offer in this simulation tool many all the components needed for designing the transceiver, from the light sources to the modulators to we offer, like, for example, different types of formats which can be used to modulate the lasers. For example, the DSP component, which is one of the things which was discussed here. We offer different algorithms in the DSP which can be used to process the data. Also, we offer some algorithms for forward effect corrections, different types of detectors, the amplifiers from semiconductor amplifiers, you can put them on the chip, to like external amplifiers, waveguide amplifiers, plus the passive components from muxes, demuxes, red waveguides, attenuators. So all of these components can be put together in a module, let's say, and simulated for your design in principle. And at the end of the day, we offer all these kind of visualizers from optical, electrical, from light wave analyzers, PRs, constellation diagrams, where you can monitor your signal anywhere in the design, and then you can manipulate the parameters of these components and be able to see, for example, synthesize your chip when you design it, or if you want to design certain chip, you can look into the what parameters required to achieve certain functionality. So all of these components is available to be addressed in a unidirectional or a bidirectional capability of the simulation tool. So with this, again, it's very short presentation here, 1 minute to finish, and we are open to collaborate with system companies, with component companies as well, to do their simulations too.
So can you also add the statistical parameters and do Monte Carlo simulations? Because one
Definitely,
of the things
yes.
you always look for is the yield, right? So
yes, definitely. We have this kind of optimization. It's part of this process as well. There is other software which is also can work cohesively with this software. It's called OptiSpice, where you can put optoelectronics components together also the you can do the chip layout as well because we collaborate with Mentor Graphic with Cadence, and some fabs we are adding up PDKs into our software tools to enable the designers as well to use the models into the simulation tool.
Okay, yeah. So I think what I can do, I can set up a meeting with our design team, right, and see if they have any interest in.
That would be perfect. Yeah.
Perfect.
And also, I sent an email to Gloria, like privately. I hope also we can collaborate with Infinera in their kind of designs as well.
Perfect. This is exactly the goal of these meetings. And also, I would like to give the word to the group Photonics from Aalto University. I can see we have a representative here. Maybe you can.
Yes, thank you.
Hello.
Hi.
How are you?
Yeah, fine, thank you.
You have something to explain, I know.
Yes. If you look at the screen, can you see everything?
Sorry, are you trying to share your screen with the green button?
Yeah. Yes.
Okay, we don't see the slide.
Oh, sorry. Okay, when that opens up, probably I may say.
Sorry. Do it again.
Is it now okay?
No, do it again, please.
Oh, sorry. Okay, I will try to do it again. Share screen.
Don't worry too much, RBK. Yes, tell us what's on your mind and what room for cooperation are you looking for in this meeting?
Don't worry for the slide.
Okay, well, I just thought of sharing some research innovation which has happened last week. Thought of sharing from one of our research group. They have made some achievement in the silicon photonics, especially the component waveguide laser, atomic layer deposited erbium laser to be precise, especially for high-speed data center. So erbium is one of the base material in a single and straightforward process compared to other competing technologies like indium phosphate or gallium arsenide or like. The key advantage is it is economical, scalable, compact, and also the erbium is not a semiconductor, does not conduct any heat, so no cooling is required. And further, the processing is relatively done at a low temperature, just 300 degrees Celsius. Why this existing optical transceiver is costlier is because it's a complex process. That is what I'm trying to show in the presentation, and nevertheless, it's okay. For example, it's 100 euro per square centimeter for indium phosphate, something like that. And we talk about here approximately is 5 euro per square centimeter. This is what we are achieved as a proof of concept last week, and we are applying for this the funding with the Finnish government here. Probably if we get through, we may just proceed further with the this technology. Why we participated here, just to make sure that if there is any industry focus is to make a joint development of research ideas. So we are open. So this is what I wanted to share. Thank you very much for that.
Thank you very much. What I have seen lately is that there is a huge growth on atomic layer deposition in companies in EPIC. If you're looking for a partnership, Aalto University is a great place to start. Also the company Atlan 3D. And we also have a lot of technologies for manufacturing of integrated photonics. So thank you very, very much. And I think we have one quick question from Photonics 42 and the final market scope of Joel. So Antonello, what's on your beautiful mind? Antonello, Photonics 42. I think what's on his beautiful mind, Photonics 42 is a new company in the assembly and packaging of photonic devices. They are looking for partnerships on wafer level testing of indium phosphide and silicon photonics. Great partnership to be made there. Why don't we go to Joel? Why don't we hear a bit about this beautiful market? Thank you very much for being with us on this beautiful afternoon. Send us away. This is the last presentation of the show. The floor and the attention of everyone is yours.
Hello, Jose. Hello, Anna. Thank you for inviting me to this meeting and giving me the opportunity to present YOLS activity in terms of optical communications. Okay, so first I should share my screen. Share. Okay, can you see my screen well? Okay. So first, I'd like to introduce the YOL. So YOL provides market research and technology analysis and strategic consulting. We have developed a unique understanding of technologies that enables us to accurately evaluate the markets, the solutions, the emerging applications and strategies. So the production team of analysts is based in Lyon in France and has three divisions: photonics and sensing, semiconductor and software, and power and wireless. And you can see the fields we cover in our reports. Now I'd like to share with you our latest product that were issued just recently: optical transceivers for datacom and telecom, silicon photonics, and the VCSEL market for all type of applications. So now I would like to start with the technology roadmap. So the roadmap shows the evolution of the transceivers used in datacom and telecom along the bandwidth increase. So the new form factors are increasingly universal, and they are designed to reduce the size and thus power consumptions. Inside the modules, the optics and integrated circuits are getting closer together to enable higher data rates and higher bandwidth. Yeah, different working groups are working on the standardization of the new form factors for datacom and telecom, and the leading optical manufacturers have already unveiled their latest 400G optical transceivers for OSFP, CFP8, and QSFP-DD. Yeah. COBO technology is quite new and is in our roadmap, but still require the standardization as we all know. Yeah, the industry struggles with the throughput and the data rates of all optical communication equipment, as well as modules that don't grow as fast as the traffic of the current and as well as new applications. So the silicon photonics is the promising solution for enabling new data rates. Also, although the silicon photonics is quite well developed today, the industry standards, supply chain, and the compatibility with the whole ecosystem is need to be established yet. Yep. Now I would like to share some market data of datacom optical transceivers. So the revenue generated of datacom optical transceivers reached out around $4 billion in 2019, and is expected to treble to around $12 billion by 2025 at CAGR of 24%. Yeah, then this very high growth will be driven by adoption of much more expensive optical modules next years that they will be based on coherent technology and will migrate from long haul applications to short haul applications. However, the COBO technology is still very emerging, and as I said, it needs standardization. So we can see today some proprietary solution on the market, but the COBO could, in high volume application, could enter the market maybe in 2-3 years. Now I would like to share with you some recent M&A activities for both platforms, IMP and Silicon Photonics. So high level of integration of optics with silicon integrated circuits lead to investment by system vendors like Cisco or Nokia. And however, today we still see that the strengthened positions of traditional vertically integrated companies which are involved in IMP technology platforms. In case of Silicon Photonics, I would like to give you an example of Cisco. Cisco has been preparing for the future as its customers transition from standard chassis-based systems to pluggable module compatible systems, ecosystems with switches and routers. And when the typical vendors of optical systems lose their exclusivity on the market today, and in coming years, when the optical interconnect from chip to chip will be required, the Cisco and the similar companies need to bet on the right technologies such as Silicon Photonics. And they cannot rely on competitors from Broadcom or Intel. Okay, so that's it from me. Thank you for your attention.
Thank you very much for a great presentation, and thank you for closing the event the way it should be. We have a lot of room for cooperation. For me, it was great because, first of all, many of you are very close friends of mine, and the others are soon to become friends of mine, very friendly, and I'm hoping I can start traveling again as soon as the whole virus is over. I am sick about taking notes. I take a lot of notes. My wife is crazy. I was taking notes at my wedding. I'm going to show you what the kind of notes I took today. For me, this meeting was very interesting for me, try to find out opportunities in the supply chain. And I think at some point we got in there when we started talking with Gloria, with Tim, with Radha about their challenges, and we understood that there is some room for materials in the heat dissipation. There is definitely some room for optics for high temperatures, and in telecom datacom we call high temperatures 130 degrees centigrade. We see some tendencies, we see some good ideas of intermediary steps, of CPO or intermediary step, or in the future. It has been a lot of discussing that, but that was not the purpose of the meeting. The purpose of the meeting was to work together. And I have seen in the Zoom channel and also in your private WhatsApps that there is a lot of room for cooperation. Many of you have set up one-to-one meetings. So all of you, please stay for the one-to-one meetings. We have arranged separate Zoom rooms for you. The ones who are interested about the one-to-one meetings, you can also stay. But for me, from Anna, and from the EPIC team, I would like to thank you for a great discussion. Thank you for great 2 hours. I hope you continue the follow-up. That was important. And from me, from Anna and the whole team, goodbye.
Thank you.